Hi, today we've got another interesting bit of formerly expensive lab kit. This was thanks to Dave at a local university who are throwing this out because apparently it needs a new X-ray tube and that was going to cost about 20 grand, so they thought it probably wasn't worth it. It's about 10 years old and basically it's a very, very small CT scanner. This is aimed at medical applications and it was being used for scanning teeth and small parts of bone. Basically what we've got here, the sample goes in there, so obviously you can only scan very small objects. And basically this assembly moves up into the X-ray head here. It can be rotated in that direction. There's a lead screw, a very fine pitch, like a 1/2 mm pitch lead screw that moves it up and down here. I think there's probably another motor inside there because there's 4 motor control boards. I can't see where the 4th motor is. And there's this sort of basically slides across to provide another axis of movement. And this came with a slightly ridiculous computer system. This is an HP Integrity 2620 server. This was running OpenVMS, and it also had this big array of 8 320 gig SCSI, Ultra SCSI 320 hard disks in this extra external storage array. I suspect that the original software may have dated back from when they used like DEC-VAX type systems on here, so this was maybe the only system they could get that still ran that operating system to run the software. It seems a little bit overkill. Obviously it probably needs quite a lot of processing power to do all the CT calculations, but this using a sort of huge server with dual redundant power supplies does seem slight overkill. System's about 10 years old. I mean, one thing that's very noticeable on this is just almost ridiculous build quality. Even, for example, these the panel locking keys. They've got these really nice sort of very solid locks with these sort of high security key profile. Just all sort of super nice build quality. We've got these EMC gaskets around all the doors and all the side and back panel. And there's actually they've actually machined the surface down from the aluminium extrusion to make contact with those. So you've got super nice, I just unclip these because I had to take the doors off just to reduce the weight a bit to be able to get it on the bench. It's ridiculously heavy. And sort of lots of nice sort of custom cable looms, or nice sort of heat shrunk ends, these sort of plug-in connectors to disconnect stuff, and this sort of 3 rack down the side with all the electronics, and sort of fairly expensive looking motor. I'm not sure if that's a stepper or a servo. And this sort of nice ball screw for this horizontal axis motion that moves the whole X-ray and detector assembly side to side. And we've got this sort of fine pitch vertical lead screw. That's the main reason for that, I think, is just to get the high vertical scanning resolution. And then there's just the aperture there that this goes through. And so I think there might be somewhere, I think there must be another motor somewhere, because there's these are the motor driver boards, and there's 4 of these. And also the end stop switches, they use these inductive proximity sensors, these sort of industrial sensors, and they've actually got these at both ends of the travel. And again, on the vertical axis here, there's one there, and there's one down there. And again, I think these are inductive sensors, and there's a screw there that they detect. And also just the general construction. I mean, this is like 20mm thick solid aluminium slab that the whole thing's machined out of. Obviously some of that's going to be for mechanical rigidity. This apparently does do scans down in the order of sort of tens of microns resolution, so it needs to be very solid mechanically. So you've got these massive great support bars on here. A slightly interesting thing is this base is actually made out of about sort of 3mm brass sheet. I'm not quite sure what's so special about brass, unless it's maybe to do with X-ray shielding. The doors and the lid, they've actually got a sandwich of, there's like an aluminium sheet and then a chunk of lead. That's about sort of 4mm thick lead sheet. And they've got that in the side doors, and also basically everything up to about sort of here. So you can see it's partly across here and then partly on the back panel. And so all the back and side panels have these key lock for access. There isn't really that much that you can get out from the other panels, but Seems again somewhat overkill to do that rather than just screwing it down, because I don't think there's actually anything you can really usefully access on any of those panels. So it does seem a bit silly to have key locks on them, as opposed to normal screws. But obviously they weren't too bothered about how much this thing cost, clearly. Now I have actually tried running all this system up. It took a while just to get the whole thing to boot. I had to juggle some memory modules around to get the server to actually start working, but after sort of getting the software up and running and then it waiting like half an hour for the tube to warm up, it then sort of said that almost anything I tried doing, it sort of bombed out with an error to say that there was some issue with the tube. I think it couldn't maintain the current it was trying to, and then sort of the software sort of fell over, and then you have to wait another 20 minutes for it to do another warm up before you could try anything else. So I'm pretty sure there's no major mileage in getting all this up and running. One interesting detail on this is the only door that you'd normally open in normal operation. It's got this interesting interlock system. I'm guessing this is a sort of a special shape to make it difficult to bypass, but as well as being a switch, this is also a lock, so that when it's taking it actually locks the door so you can't open it. As on this side we've got the electronics rack. There's a few PCBs and these sort of very nice latching PCB latching eject handles. So we've got, this is a main CPU board. This whole thing runs on a SCSI interface to the workstation. So we've got the SCSI cable here. We've got two cables marked hotlink. These will be high-speed connections to the X-ray sensor. Hotlink is a sort of high-speed serial communications protocol that can run over coax or fibre. There's a Freescale MPC 55 microcontroller that's about half meg flash, PowerPC based micro, some IDT memories, Xilinx Spartan 2 FPGA, and some just sort of bus switching logic. Some interesting packages on this. I've never actually seen SO packages or SSOP packages quite this wide before. I think these are sort of 32 odd bit bus switches. They're just in that package, I think, just to simplify the PCB layout so it like flows through from one side to the other. And these are the two Cypress chips with the transceivers for this hotlink protocol, and there's an isolation transformer there. Also there's some CAN bus transceivers here. I'm guessing they may be using CAN bus for the motor control stuff. There's a little DC-DC converter on a little subboard. I'm guessing that's probably for the FPGA. Not a great deal else on here of interest. A connector on there, I'm sure that'll be some sort of expansion connector for option boards that can plug onto it. And this next board up here is basically full of opto-isolators, so I'm sure this is just going to be interfacing to all the various switches and other bits and pieces in here. There's a few, couple of DC-DC converters, lots of optos, HCTs and buffers. That looks like there's maybe some analog interface stuff there, perhaps some analog sensing of some sort, but guessing those are probably protected MOSFETs or something, like 5-pin devices. And for probably switching various, there's I'm guessing inside the X-ray head there's probably going to be some things like beam shutters and maybe one or two solenoids in there, so that may be what these are for driving. These might also perhaps be switching the power to the motor drivers as well, I don't know. And down here there's 4 motor control boards. There's a big sort of chunky, sort of 4 mm thick solid aluminium heatsink on the top with all the various power transistors on it. Sort of insulating sheet on the back. And these boards are made by Phytron, so these are sort of off-the-shelf controllers there, stepper motor drivers. Sort of very discreet. There's an Altera PLD there, but everything else is all sort of discreet. MOSFET drivers, comparators, analog stuff. And all those boards just plug into this custom-made back plane. I'm sure all the back's just going to be all the connectors out to all the... and surprisingly, the top panel that's got these LEDs on is just sort of hardwired into a plug-in connector in the back. I would have thought it would have been neater and possibly not much difference in cost. I've actually just done that as another PCB with just the LEDs on it going into a plug into the back plane. Seems a bit odd why they would have hardwired that. Obviously they weren't too worried about cost. taken all the panels off and all the shielding out of the top, so it's just about light enough to spin around on the bench to take a look at the back. This is the back of the rack unit. It's got this. So we've got this sort of shielding bulkhead type arrangement where wires come in and their shields are just clamped within these little quite neat little pressing clips. That's quite a, I've not seen that before. I'm guessing this is some sort of off-the-shelf sort of shielding kit that you can get for these racks. I've not seen it before. It's quite a neat neat solution to be able to sort of get good shield continuity to the ground, but without having to sort of pass them through a hole or use cable lands or anything. It's quite neat. So these will just go, all these cables just go to various plug-in connectors on the back. And this custom backplane. And a big 600 watt power supply in the back. Guessing a lot of that will be to power the X-ray generator. This is one of these Lambda modular ones which we've seen a couple of times before. If you want to see the inside of one of these, take a look at the Leica microscope video. I think there's another one maybe in the broadcast equipment video as well. It's quite a clever system from implementing modular power supplies for sort of different permutations of outputs. Got a bit of a cable management nightmare in here. This is a fairly ridiculous chunk of cable, so put some slack and just sort of folded them up into this huge bit of trunking on the back. That's a pretty tight fit. Right, we've just about got it to the stage where we should be able to get this main guts out of the frame. So there's lots of attention to shielding. For example, this is just an air filter to let the air go out, but that's got shielding mesh over it. In the top cover again we've got this RF gasket, and the you see they've put a gap in the paint on there, so they were very serious about shielding on this thing. I mean, obviously the centre itself is sensitive, but that's on going through coax cable, so it's probably just generally MC and belt and braces, stop anything getting in or anything getting out. But I'm not sure I've ever seen quite as much attention to detail. But then again, this is, in terms of sort of big bits of expensive kit, this is relatively recent compared to a lot of the other stuff I've taken apart. So maybe that's one reason. Obviously you've got faster processors going on, quite a lot of data flying around, and say some of the older bits of kit taken apart were back from when there weren't so many regulations on that sort of thing, so that's probably one factor adding to it. Still really puzzled as to why they've used brass for this baseboard. Seems a slightly odd, you know, why wouldn't they use aluminium? The lead shielding seems to be a sort of a sandwich. They sort of got two sheets of aluminium with a lead sandwich between it. I don't know if that's like a standard material that you can buy in sheet form or whether they custom make it, but obviously a lot of that's down to, obviously lead is quite a sort of soft floppy material, so the aluminium keeps it nice and rigid and flat, but also keeps the lead away from, you know, avoids any lead sort of getting in anywhere from the point of view of being sort of slightly toxic. So it's probably a way of just making the lead into a much nicer to handle material. Right, so I've got all the major bits out now. This is the X-ray generator, this is the detector assembly over here, so the sample goes up into here. This horizontal lead screw assembly is basically positions the sample, yeah, controls the position of the sample in the filter. That's effectively providing different amounts of geometric magnification from, you know, the point source of the X-ray beam to the detector, so that the closer, you know, the further you are to the source, the more magnification you get. And then we've got the vertical thing, which is does two things. Firstly, it actually moves the sample up into this assembly, but then it gives you this very fine vertical control. According to the documentation, it will do slices down to 6 microns. So you've got like I haven't measured it, but that feels like probably about 0.5 millimetre lead screw, and then you've got probably a 400 step motor. So that gives you 800 steps per millimetre. That obviously gives you very fine resolution on that slice axis, and then this stepper motor here just rotates the sample to within each slice. Now the actual detector assembly and sort of where the sample goes is surrounded by some very heavy brass, so there's these two plates either side of it. Then the base plate, this is what's actually attached to the sled. So we've got the detector assembly here on the right. There's also this is where the fourth motor is. You've got here you've got sort of thin slit from the microwave, the X-ray thing. I'm not quite sure what metal this is. This clearly might be stainless. Not quite sure they they haven't used brass like they've used everywhere else for this. This motor then just moves this sort of vertical piece. I think that's just controlling the width of the beam that it allows through. It sort of gradually sort of closes in from this side, so that probably controls the beam width. So again, gives some control over resolution. Right, so this is the back of the central assembly. We've got our two hot link cables for the high-speed data. Interestingly, it doesn't look like there's any control inputs to this at all. This connector here goes straight to the power supply, so in terms of possible repurposing, that's actually good news, although it could be that this is a two-way link and there's data backwards and forwards, but it would be quite nice if we've just got like something really simple like clock and data that we can look at from here. I'll have to figure out. I'm guessing this sensor will be possibly made by someone like Hamamatsu or someone, so we might be able to find some info on it. There's also this fan and heatsink on the back. Now that suggests to me, I wonder if there's actually a Peltier cooler in there to reduce noise, to get the maximum sensitivity. I can't think why you'd need that amount of heatsink on something that's just a sensor, unless it's something like a CCD array that's got very high sort of clock rates that's burning a lot of power driving that, but we shall see. Nothing too exciting so far. Okay, so what we've got here, we've got some sort of detector with this. Well, it looks quite chunky. This doesn't feel like it's solid. I'm not sure that's. It looks like it's some sort of folded can. So I'm guessing there's going to be a scintillator on top of the material. It could be this is some extra sealing or something. Yeah, and this is from our old friends Hamamatsu, not surprisingly. It's about a 1K by 256 CCD image sensor. So this will be some sort of scintillator assembly. Looks quite thick. I wonder if it's perhaps a scintillator here and then perhaps some sort of fibre optic array or some sort of optics. Or maybe it's just perhaps some shielding and the all sorts of X-ray filtering and the array there. I suppose the other thing it could be perhaps is some sort of scintillator here and then some sort of X-ray shielding. Perhaps there's some little fibres or something going through. And in this top part, I've got a Altera Max CLPD. These two are the Cypress Hotlink transceiver chips. So there's not a great deal in here. So on this board, this is a Burr Brown VSP 3100. This is a CCD front end chip. It basically does everything for processing CCDs, including the HD converter. So that's providing digital data out here. There's some just AC series stuff here and some power supply bits here. So this is all setting up all the biases and voltages for the CCD. Then on here we've got the obviously we're taking the digital data from the HD into this PLD, feeding it out through these hotlink transceivers. It looks like there is a two-way link. There's a transmitter and a receiver on both of these, and there's an AD 78A1. That's a DAC, so that's probably going to be producing some of the analog voltages to drive the CCD. But apart from that, that's all sort of fairly straightforward. Just taking high-speed data from that CCD and spitting it out serially out of these ports. This is all mounted in this sort of massively chunky casting. I mean, some of this might be to do with X-ray shielding, but I think a lot of this is just mechanical rigidity, because this whole thing is sort of very solidly made. So this is really heavy, it's a massive chunk of brass here. So I think the brass must be something to do with shielding, or yeah, also sort of preventing scattered X-rays bouncing around inside. But it's very obvious, you know, there are two obviously different materials here. I really don't know what this is. It looks a little bit too dull to be stainless, unless it's some unusual grade of stainless. But it sort of clearly used a different material for some reason or another. I'm not really sure what it is. And this is just crazy heavy. This is way heavier than steel. Slightly magnetic, but nowhere near as magnetic as steel. So unfortunately I no longer have an X-ray fluorescence spectrometer to figure out what this stuff is. But just go sort of the really crude approach, just measure the density. So the density of this is 17,400 odd kilos per cubic metre. So let's just have a look at some metals that it might be. So if we sort of just look down this list, it's, you know, like about twice as heavy as most of the more common metals. Gold is 19,000, so it's clearly not gold. Iridium, probably not iridium, it's probably a little bit too exotic. Osmium, again, that's probably a little bit too exotic. Platinum, yes, it would be nice if it was platinum, but clearly not. Plutonium, yeah, it probably isn't plutonium. And uranium, again, it's not far off, but I think tungsten is probably the most likely, but it's lighter than that, so it's probably an alloy. Also, tungsten isn't magnetic as far as I know, but it's also very difficult to machine, so it's probably an alloy. So just looking up tungsten alloys, and we find, yes, there are actually some which are alloys with some iron in them. One of the main reasons is to actually make them machinable. And here, yes, we see some here which are pretty much spot on, 17.5, so that's 17.45 is what we measured, so it's clearly going to be a tungsten iron type alloy. And in fact, looking a little bit further, one of the applications of these alloys is, you know, it's specifically designed for radiation shielding. It's more dense than lead, so you can produce stuff in a smaller space, but also it's machinable as well. So if you're, you know, if you're making structural parts like this, it's clearly a better solution than lead. So yeah, that's clearly what it is. Right, time to look at the X-ray generator. This is quite a compact little unit. There's external beam shutter. That might be something like a vacuum seal off or something. Hard to say. That's going to be that'll be a beryllium window to allow the lower energy X-rays through. Got a little sticky tape there, not quite sure. Maybe that's just to hold the window in place. Seems a bit of a bodge, but so the reason this thing was scrapped was that this thing's not putting out enough energy, and they say it would cost about 20 grand to replace. So I suspect a lot of this might be potted or encapsulated or something because of the high voltage. So it's rated up to 90 kV, so there's clearly going to be some fairly solid insulation in there. And there's a sign on here saying may contain a chemical known to cause cancer, birth defects or other reproductive harm. I'm guessing that's probably referring to the beryllium, but when I was in San Francisco, pretty much every building I went into had a sign saying that outside, so not sure how useful that warning is. So we can see something in here. We've obviously got the tube underneath. This looks like it's in a sort of lead cylinder. PCB on top. A few little bodges going on there. Even there's a bit of perf board in there. Yeah, that's not very pretty. I wonder if maybe that's setting some fixed values for things. Perhaps there's some version where you can adjust lots of things through this connector, and maybe that's just setting some fixed values for some of those. But that does look like a little bit of a bodge. This is part of a sort of flyback transformer for the power supply, and that's sort of going straight into here. So this is, there'll be the high voltage rectifier multiplier inside here. There's another sort of rubber coated block up here. That may be some feedback sensing, sort of measuring the output voltage, or maybe measuring tube current or something. Not sure how much further we're going to be able to get into here, but let's have a go. The electronics on here look pretty straightforward. There's just some power supply stuff. There's some SG3525 regulators, so there'll probably be one for the main high voltage source, possibly one for the filament supply, and maybe also because the microfocus tubes have like an electron gun type arrangement, so there's probably another supply for some of the electron gun potentials. Actually thinking about it, this block here might actually be for generating some of the intermediate voltages for the electron gun. And apart from that, it's just some analog stuff, so there'll be some monitoring sort of to measure beam current and possibly output voltage. Just all sort of fairly standard analog stuff, so nothing particularly surprising. So, that's interesting. This module here actually is connected to this output thing. Now, I assumed this was the beam shutter, but maybe it's something a bit more involved than that. I suppose it could be sort of the electron gun sort of going down there, and there's a sort of target here. And some other stuff back here. I don't know, it's a bit intriguing. Yeah, actually this is like a CRT base type socket by the looks of it. Yeah, so this is clearly something sort of vacuum physicsy, so it could well be that that's either the electron gun or something to do with focusing it, perhaps. So I'm not sure how much further we can get into this, but we'll certainly try. Obviously there's no point in trying to x-ray any of this because that's just big chunky lead, so it's not going to go anywhere. The back of the board again, we can see this. I suspect this is possibly not quite so much a bodge wire, but I'd imagine that a lot of these things are customised for different users, so it may well be this is sort of more of a sort of customisation to a particular requirement rather than necessarily a bodge to fix design errors on this, but obviously there's no real way of knowing. There's this coax on the back. This feels like it's Teflon or something, and this was connected down to a tab here, so I would think this is probably sensing for sensing the beam current, which is typically on the order of sort of up to a couple hundred microamps. So there's a test point there as well, so there's probably going to be some precision resistors here, so this is going to be just an amplifier to provide an output to measure the beam current. The way that X-ray tubes are typically regulated is they have a constant voltage supply, then they adjust the filament current to get the required beam current, because the voltage provides the characteristic spectrum of the X-ray, so you want that to be constant. So the only way to adjust the current is then adjust the emission of the filament, although again, because these have got an electron gun, there might be other ways they can do it via controlling some of the electrodes on the electron gun as well. Don't know enough about the electron physics to know exactly what they do here. So we've got the tube and high voltage assembly, and it's looks like it's wrapped in lead sheeting, so hopefully we'll be able to peel some of this off. Starting to get that characteristic oily smell that I've noticed when taking X-ray stuff apart before, so obviously there's going to be some probably insulating oil inside here somewhere. Right, we're down to right, this is looks like some sort of cast material. I'm not actually sure whether that's, oh, it is some sort of cast resin or something. Yeah, it does look like the sort of, it might be that this is an enclosure and everything is just sort of placed inside it rather than actually encapsulated, but I suspect things might get a bit oily in a minute, so let me find something to put this in. It's already getting too messy. Oil. So that's the actual tube assembly. Just a spring contact down there to make contact. I've got a suspicion the whole rest of this thing is potted, which is not going to be very useful, but there's another cover on here. Nothing in there, so I'm guessing that's maybe an option for some other variant. So it looks like this entire thing is the voltage multiplier. Obviously for 90 kV you need sort of quite serious insulation. So there's this screw that connector came from, so I wonder if maybe there's an internal divider network to provide voltage feedback. Here's an image from one of the patent numbers referred to on the label. There is a voltage divider inside which goes to that terminal, but interestingly the main voltage multiplier is fed from the centre. Not something I've seen before. It might be quite common. I've not really looked at too many of these things, because long voltage multipliers get sort of increasingly inefficient because of things like stray capacitance and so on. So what they've got this floating drive from the transformer which they're feeding into the centre of the voltage multiplier, so you're effectively generating a bipolar supply and then grounding the negative end to produce the high positive voltage. Yeah, this thing's totally solid. Tried x-raying it but couldn't see anything, but I think there might be scope to have a little bit of fun with a 90 kV voltage multiplier perhaps. Right, so just looking at the patent for this thing, this is the actual electron source here, and this is the target, sort of big chunk of copper here for heat conduction. And so this is the anode, so you've got the positive connection going in here, and there's the lump of copper, and there'll be a tungsten target on the end of this, and sort of the electrons come down here, bounce off, and one of the key things is to keep the path between the electron gun and the target and the output as short as possible to keep the focus as tight as possible. Now this tape here is actually holding what looks like a sheet of aluminium. Now aluminium is quite commonly used as a filter material on X-ray tubes. I think it's to get rid of a lot of the lower energy X-rays. Most tubes do have some aluminium filtering on it, and then there's the actual beryllium output window. So this whole assembly is all sort of welded together, and that'll be the vacuum seal. I'm guessing that copper might actually be a cover over the actual seal, or it could be this is glued or brazed over to provide, obviously this thing will be at a high vacuum. And this is the characteristic sort of slightly brownish glass that you tend to see in X-rays, which I believe is to make it very, very slightly conductive, so that you don't get charge build up on the glass surface, which can mess things up. So it's just to provide a very, very high impedance sort of drain away to avoid that. And you can see here we've got this glass to metal seal, so it looks like it uses a couple of different interfaces. So these would be very carefully chosen materials to match the expansion rates and provide a vacuum tight adhesion between the glass and the metal parts. A little hand engraved serial number on there. So these are made in fairly small quantities, so these are all probably mostly hand built. Alright, so we've got the basic info from the patent. I don't think it's really worthwhile taking this thing apart any further. I don't think we're going to see anything particularly interesting. It's be a quite nice little ornamental piece, I think. So I dug some of the compound off of this, as pretty much as expected. There's 3 ferrite pot core inductors, or transformer things, high value resistors, obviously a voltage multiplier here, so this will be generating one of the high voltage supplies for the electron gun, plus various other odds and ends. A couple of diodes that you can see in here, big 1 kV cap here, but I'm not going to bother digging the rest of this out. It's a bit of a pain to do, and it's not going to reveal anything particularly exciting. So let's see if this power supply will do anything interesting. I've hooked it up back to the driver board. I haven't put the driver board in its original position because the far end would end up sort of quite close to the high voltage end here, so I'll just hardwired that in. And I've got this running on the bench without the transformer connected, and just put this bodge wire in to make sure this switch mode control was oscillating, so that's actually giving a nice 50% drive to the 2 output MOSFETs. And I've just connected ground wire to here. It's about a 2-inch gap, so if that's 90 kV it shouldn't have any particular trouble jumping that. Hard to say what's going to happen here. It is a fairly low current supply, so there could be quite a lot of internal current limiting, so it might be a little bit pathetic. Diode multipliers don't tend to like spark discharges, so it might well break over once and then just die. Let's find out. It doesn't actually appear to have killed it, so let's maybe try putting some insulation around that pipe and see what happens. Now, I've just put some fairly thick wall acrylic tubing around that, so hopefully that now won't break down at that corner. I might get a bigger spark out of it. Oh yeah. So that's jumping about 35 millimeters. So make sure I discharge it before I touch anything. That's starting to flash over down the bottom, so I think I need a longer bit of insulation in there now. Right, it gaps up to about 100 millimeters now. See if it'll jump that. It's breaking down at the bottom again now. Right, I've just filled that with oil. It's a bit messy, but it should work. The next weakest link is probably at punching through the acrylic. I don't quite know what the breakdown voltage is, but let's see what happens. It's not quite making it. You can actually, if you look closely, you can actually see some streamers coming off of that top electrode. Well, that was quite impressive. I was actually quite surprised that that didn't just blow up. I think maybe we'll have to keep that for future experiments, I think. Okay, let's take a quick look at this sensor interface. So it's got these two coax leads running this hotlink protocol. So I'll just powered up the backplane and the CPU board. Incidentally, I've had a look for any interesting serial stuff on this board. There is actually a Max 232 on there that goes to a connector on the back plane, but there's no data or anything. Coupled probe, sort of very short ground leads to probe high frequency signals on this. So each board's got a transmitter and a receiver on it, so it's obviously a bidirectional interface, although I'm not really quite sure why they'd want a high-speed interface to the sensor. So I'd imagine it's pretty much all data coming back. But again, they clearly weren't too concerned about cost on this thing, so maybe they just thought it would be easier just to put a symmetrical interface there, even if they didn't actually end up using much of one half of it. Right, these are the signals coming to and from the top traces from the CPU board to the centre, and the bottom trace is the sensor data output. So I'm just triggering on that sucking trace for the moment because that's the one that's got the most obvious data. So we've got this sort of fixed pattern, which is presumably sort of bus idle or zeros, and then sort of bursts of data. Unfortunately, when you've got data like this, it's actually very difficult to look at it on a sort of macro scale, because I actually tried to figure out some ways using some of the clever trigger modes on this scope, and it's actually quite difficult to do because of the serial nature, and there's no explicit hardware in there to decode this. So if we actually look at the what's coming from the CPU board, so we've got a pattern that's mostly static. If we turn the intensity right up, we see we do get these very occasional triggers, which will be the telling it to actually start doing the conversion. We can get an occasional trigger on that pattern, but it's very difficult to say only trigger when you're not seeing this pattern. There's a few things you can do which are of sort of limited usefulness. For example, you can set up a mask. So we can set up a mask to make it stop when it sees something that falls outside there, for example there, but that's not really a sort of repetitive trigger. It doesn't really help us that much. We can see, but we can actually sort of move this, and we can actually see that it is a different pattern. So if I sort of just move this to match it, we can see we've got a different data bit here from the original data where we set the mask up. So, but yeah, you can get odd individual words like that, but it's not particularly viable for doing sort of reliable triggering on that. I'm not really sure there's any sensible way of doing that without decoding the data in detail. But fortunately, we've got access to these transceiver devices, so there's no particular need to decode that data, and we can just trigger on a data line that I found that was transitioning when it was sending one. Every time it's sending the command, so that's just it looks like you can actually see, if you look at this top trace now, we can actually see, this touchscreen is slightly too sensitive. Turn it off. So we can actually see some slight differences in the pattern here, which is, so obviously it's writing a byte, then that's being then sent over the serial interface to actually then trigger the sensor. But it's actually quite a long way after that we actually get the sensor data back. So if I just probe the received data from the receiver chip, you can see we've got about sort of a couple of milliseconds delay before we start getting data. Then we get this big burst of data coming back from the sensor. And each of those is about a millisecond, so I'm guessing that's probably one line of data. It seems to be sort of fairly regular chunks. And yeah, that's so each line was about a millisecond. We're getting, it's about sort of 270 odd milliseconds total. So yes, there's 256 lines in this sensor, so that'll be each of these will be one line of sensor data. So, and it probably would be feasible to figure out how to use this sensor. If we use these hotlink transceiver chips. Incidentally, these are fairly obsolete and somewhat expensive. I don't know if they were always expensive or they're just expensive because they're obsolete now. But basically, they sort of be a simple sort of way of converting sort of parallel data into a fast serial stream. And nowadays, you probably use LVDS on an FPGA or something to do a similar thing. As you can tell, if only because of the big sort of chunky PLCC packages, that it's fairly old tech. I don't have any particular interest in getting this sensor working. Yeah, I don't think I'll spend too much more time playing with this, but it is sort of potentially usable. So just taking a quick look back at the what's in here. There's pretty much just this FPGA, which will be doing stuff like generating some of the CCD timings. But in terms of the data that's coming back from the CPU board to here, I can only imagine there's a DAC here. There's some setup DACs inside this CCD processor. So unless they have to do something like update the DAC on the fly, sort of on a line-by-line basis, it does seem a bit overkill using that high-speed data link coming back. But say, if they're not too worried about cost, maybe it's just a case where just keep everything symmetrical and simplify it a little bit. So yeah, and it probably would be possible to figure a lot of this out. I think the problem is that because I couldn't get any major sense out of it talking to it through the SCSI interface from that system, it's hard to know how much setup data this is like to send back, and not being able to do that would be quite difficult. But say with the sensor itself isn't sort of super interesting, so don't think I'm going to be pursuing doing anything else useful with this thing. Okay, I couldn't resist the temptation to pull this sensor apart. So at the top we've got a layer of aluminium foil, which I'm sure will be filtering, and then sort of on the bottom of that we've got this scintillator material, sort of yellowy stuff. Let's just see if we can make this stuff glow in my mail room X-ray. Now, so we've got the sensor die here, but I'm not quite sure sort of what's going on with this thickness. Whether they've this is a lump of metal and they've mounted the sensor sort of high up on it and using this as sort of perhaps heat sinking. Whether maybe this is even some sort of like fibre optic array, and it could actually be the die's actually down here, but there's just fibre optics pushing the light from here down to here. It's a bit hard to tell really. And from the top it looks like the sensor's very close to the top surface, but if that's the case, what's the deal with this great big thick okay, this outside isn't solid metal, there's just a foil around the outside. It does seem to be a fairly solid material, so I'm sort of beginning to think this is actually a light guide type of deal. Let's look at, there's a line of epoxy, it's clearly been epoxied to the top of the chip package here. Okay, so I tried separating this light guide from the chip, and it's sort of basically taking the chip with it. So this is just the sort of cavity of the package of the device. Obviously they've used the device without the windows, and it's got this block of light guide material which it's been machined down just here to get it inside the chip cavity. But so this is a sort of light guide type material, which is sort of a large number of sort of effectively parallel fibre optics. So it just takes a flat image and projects it up onto the surface. This is quite commonly used on imaging applications, where you need to sort of basically move an image from one place to another without any sort of focusing type optics. Interesting, there's actually a natural mineral that does this. It's a mineral called ulexite. I would imagine that this is a manufactured thing rather than using this natural material, but it's quite interesting. There's actually a sort of something you can find in nature that does the same thing. It's quite cool. Now, compared to the sensor in my Faxitron X-ray, where they basically took the sensor and put the scintillator material directly on the die, I think sort of the reason for doing it this way is probably sort of just practicality, in that because this is a fairly low volume specialist thing, instead of having to get some really exotic special fabrication process, they can buy these sensors as is, but probably without the window, or maybe even they take the window off themselves, add this and then add the scintillator, so it's a much sort of lower tech overall process to achieve sort of pretty much the same thing. It might also be the case this material might provide also some X-ray filtering as well to reduce the effect of X-rays on the sensor, so that might be another factor. So another bit of interesting high-end kit there. So it's a pity I didn't manage to do some CT scans of chips or anything, which might look quite cool, but at some point I do plan to experiment with that using my Faxitron X-ray, so that might happen at some point. I think that high voltage power supply might also provide some future entertainment as well.